Welcome everybody, and thank you for attending today's seminar. As you know, this is a seminar within the PQ Cifris initiative and the PQ Cifris seminar series on post-quantum cryptography. In fact, as you know, PQ Cifris is the post-quantum cryptography thematic group within the Italian National Cryptographic Initiative, the componendis Cifris. Today, we have the pleasure to host a seminar given by Shi Bai from Florida Atlantic University. She is an assistant professor in the Department of Mathematical Sciences at Florida Atlantic University. He is also a faculty member in the Center for Cryptology and Information Security of the same university. And his research interests are in cryptography and computational number theory. She has also successfully dedicated himself to factorizing large integers and solving RSA factorization challenges. Today, she will speak about lattice-based crypto, which is one of the main areas, as you know, of post-quantum cryptography, together with code-based crypto and some other families. The focus of Shi's talk would be on the learning with errors problem, and the best known techniques for solving such a problem. Okay, I don't want to take away more time from Shi's talk, so Shi, thank you again for accepting our invitation. The stage is yours.
Okay, thanks very much for the introduction, and thanks a lot Marco and Paulo for inviting me to the PQ Cifris seminar, and it's my pleasure to speak here. So I'm going to talk about lattice algorithm for various of the LWE, which is a dominant assumption used in lattice-based crypto. Just before I start, I just want to check, is my volume okay? Is the level? Can everyone hear me?
Yeah.
Okay. Okay, so I'm going to start with an introduction of the so-called learning with error and short integer solution problem. So they are short as the LWE and the CIS problems. Okay, and then I will talk about algorithm for LWE. So not restricted to the lattice algorithm, but the other algorithm as well. Okay, and then I will focus on the relation between lattice and LWE. Talk about the lattice algorithm for breaking the LWE, which is one of the I would say most practical algorithm for breaking LWE. So from a theoretical point of view, there might be some other algorithms which breaks LWE, which breaks some variants of LWE better than the lattices. But for practical parameters that we have seen in, for example, in the NIST candidates, I would say the lattice-based algorithm are the most practical way for breaking them. So there are generally two ways if we want to use lattice algorithm for breaking LWE. So the first step is to embed the secret of the LWE into some lattice point of some lattice. That's the first thing. So we're going to have a lattice in order for us to play around. And in the second step is we need to use certain algorithm to find this lattice point, which is in general a short lattice point in the given lattice. Therefore, we need to consider the complexity, and in particular the concrete security or concrete complexity for practical schemes. So in the end, I'll give a quick summarize. Okay. So I'm going to start with the LWE and CIS problem. I know there are lots of experts in the audience working on coding theory, so I'll try my best to match this with coding theory. But my knowledge on coding theory is really fragile. So correct me if I'm wrong. Okay. I'm going to give the definition of learning with error from a matrix point of view. The theoretical definition of LW does not restrict the number of samples, which is the number of rows in this matrix A that we're going to look at. But in this particular example, I'm going to start with a matrix A, which is sampled uniformly from the QM times n. So it has m rows and n columns, where each of the number is sampled uniformly and independently modulo q, where q is some number that we pick up. Okay. And after that, we sample a vector s according to some distribution s. So this distribution can be chosen to be uniform or can be chosen to be small. And we also sample a small vector e according to some distribution dE. So here, for the problem to be well defined, we need this vector e to be somehow small, where the definition of the small could mean e has a small L2 norm, or e could have a small Hamming weight, depending on the variant of the LW that we're using. So the problem is given A and B, these are the public information, where B equals to AS plus E modulo Q. The problem is to recover S from or E given A or B. So in the coding language, this is more like the S is the message, where A is the generating matrix, but in the column form, where E is the error and B is the transmitted code word. Of course, this E is set in the sense that it's more than the decoding radius. Therefore, there's no way that we can decode easily. Okay, and here are some example parameter. So the security of this problem, we will see that it depends on n. So we will choose n to be about the security parameter lambda. For example, lambda is 128. So we choose n, which is constant multiple of that. And we choose the modulus q to be n squared. This is just one set of possible parameters. And we choose the number of samples or the number of rows in the matrix to be n log q. We can choose the distribution ds on S to be uniform on the Qn. And we choose this distribution E on this small vector to be discrete Gaussian with some deviation about square root of n, for example. Okay. And we will also denote, just for the convenience of the discussion, we will denote sigma, this guy equals to alpha times q. And we call this alpha as the error rate, because that's approximately the ratio between this deviation versus this q. So that's just some convention. And in the picture form, I write this. So A and B in this purple color, they are public information, where S and E are the private information that we are trying to retrieve. Okay, so solving either S or E is sufficient for us to solve the other. So search version is given A and B, find S or E. Okay, and in many of the crypto proofs, people prefer to use decisional version, and that's the case where we are given samples A and B, but we are not given whether these samples are from the truly LWE or from a truly uniform distribution. So the task is to just seeing these samples, we decide or we tell whether they are from LWE or they are from uniformly random samples. Okay. Clearly, this B, if we think this as a transmitted code words, and if this E is not really too large, this B cannot be fully uniform because it doesn't cover every single element in the underlying alphabet set. So a dual problem, which is for the LWE, which is the cis problem. And here I'm going to consider a slightly generated version, which is called inhomogeneous cis problem, inhomogeneous short integer solution problem. This is really the syndrome decoding problem for coding theory people. Okay? So the matrix version of this is we start with a matrix B, where the matrix B for the problem to be hard has to be a wide matrix. So if it's a top matrix, it's overdetermined, then we can solve it by linear algebra. Okay, and there's a small secret E, and this E can be synced similarly as the E in the learning with error problems. Okay, so the relation you can think about is we multiply the left kernel of the matrix A that cancels this part, and the left kernel of the A times this E equals to the left kernel of A times B. So that gives this guy over here. So T equals to B times E modulo Q. So B is we can think it as the left kernel of A, and the T is the left kernel of A times the B in the LWE problem. So that's the kind of dual relation between these two problems. So the inhomogeneous Cv problem is given B and T, recover this little e over here. Okay. So that's the picturized description. Given B and T, recover E. And there are lots of variants of LWE, and that's really, I think, one of the reasons why it is quite complicated to consider the security of LWE, because in one regime you have some provable asymptotic method for setting up the parameter for LWE, but on the other hand, in practice, we don't want to use this asymptotic setup because simply that it gives large parameters, and we want to, shrink the parameter. So sometimes this involves the parameter to be beyond the theoretical asymptotic good setup. But in the meantime, there's no practical attack that can break them. So that's the general idea of this security for various of LWE. Okay, so the standardized setup, maybe the first two are sort of standard. You can set as uniform and E small. Small means not too small. So here means small means standard, because we will need E to be small for this problem to be well defined. So we can also set S to be small, so which follows the same distribution of E. This is called the normal form of LWE. And this is we really just change the A to be the systematic form in the coding kind of language. From there, we can make S to be small. Okay, and then E is also small. So the first two forms are quite standard, and there are some theoretical. There are lots of theoretical support for that, and there are more variants depending on the application. For example, we can make E tiny. Tiny means much smaller than the small. And for example, we can have the binary error LW where E is binary. Okay, so when E is binary, depending on the numbers of samples given, the problem can be easy or can be hard. So we will see a discussion on this. And similarly, we can have both an S and E to be binary. Again, this problem really depends on the number of samples given. We can have S really small, S really small, and E to be kind of standard. That's the binary secret LWE. So in certain applications, you want that. For example, FHE. And you can also have the variant where you want S to be extremely small. So S is sparse, its Hamming weight is low, and that you can also, in this case, you probably want to set your dimension A to be large to compensate the smallness on the S. And also depending on the numbers of samples given and depending on the modulus, the combination can give you a very, I would say, a very messy picture of this variance of LWE. And that's really something that we are going to look at. So the combinations of distributions, the number of samples gives the variance with very difficulty. Some of them can be guaranteed in theory, but some of them there's no guarantee in theory, and we should check. The best method is to check their concrete security level. Okay, and that's one of the purpose of this talk. Okay, so I just broadly divide the algorithm for breaking the LWE into three categories, okay, including the geometric method, which is the method that I'm going to talk today, which is the lattice algorithm. So it frees the LWE instance as some lattice problem. As I mentioned already, we usually embed the secret S or E, or both S and E from LWE into some lattice point and find this lattice point by some lattice solvers. But there are also two other methods, which are called algebraic and combinatorial, and these methods are pretty good from an asymptotic sense for solving the LWE problem. especially for some special variants of the RWE problem. This is a particular case. For example, the combinatoric algorithm are particularly good if you have a sparse kind of secret. And in this talk, I'm only going to focus on general QRE lattice without any structure. So if there are some RWE with some bad structure, you can actually break them easily. But this kind of structured RWE problem are not proposed in the regular way or in the canonical way, in the sense that if we just use the general RWE problem, the union RWE problem, most likely we won't get into such a problem. Okay. So the first type of attack is the so-called algebraic attacks. It starts with the Aurora-Gers algorithm for the learning with parity problem, the learning parity knots problem, which I'm sure the coding people would be more familiar on that. So clearly, it was originally designed for the case that your error is small, and it's natural that it caters for the case of the so-called binary error RWE. So in fact, if the error of the RWE is binary, and we already have a polynomial time algorithm if sufficiently number of samples in the RWE are given. For example, m equals to order n squared. I just want to emphasize that actually such number of samples is already not small, in the sense that if you look at many of the NIST proposals, the number of samples given, they are just a constant times n. For example, m is usually 2 times n or 3 times n for some small constant, and therefore, and in many of the NIST proposals, the error are not binary at all, and that's really where the difficulty of this problem comes from. So the number of samples is also restricted. Okay? So if the number of samples is reduced to almost a single linear factor with respect to n log n, then the problem already becomes much harder than the polynomial. It becomes sub-exponential. Okay? And for m, which is close to n, so there are some reduction of this binary error RWE problem. On the other hand, it's reduced to the SIVP gamma problem with some polynomial gamma, but in a reduced dimension in some sense. So maybe the problem for binary error and for small sample is not really that difficult. But on the other hand, we don't have an algorithm to solve that in this running time. It just means this problem is harder than that. Okay. And on the other hand, if we allow to slightly increase the binary error to be something I call the tiny. Tiny means it's between the range of binary and small, which means standard. We have a trade-off between the size of the error versus the running time, where the running time is 2 to the order tilde. Since this order tilde subtrahes a logarithm factor of this, so I just ignore that, of alpha squared q squared, where alpha q was the deviation we mentioned before. So therefore, it was already sort of for sub-exponential if alpha q is smaller than square root n. So it's mildly sub-exponential if they see it's smaller than that, with enough number of samples that I didn't specify really here. And if we have the standard error RWE, if we plug in this formula over here, the running time is actually already 2 to the order n, something like that. So for standard the RWE problem, this algebraic attack still use full exponential time. Okay. And so in the second type of algorithm, which is so-called the combinatoric type of algorithm, essentially it follows the BKW-like algorithms for the RPN problem as well. Okay, so for example, for the RPN problem, when the modulus Q is 2, clearly there are less things to do the collision. So this BKW algorithm, we are hoping that there's a lot of collisions on the A's. So we need the underlying space to be small enough, or the number of samples to be large enough in the same time. So therefore, we need a sufficient number of samples. For RPN problem, we need exponential samples, and it runs in sub-exponential running time. Okay. If we have similar phenomena as before, if the number of samples is restricted, and the running time will become larger. Okay. And there are some improved algorithms for the case of LWE. If we barely just use this algorithm on LWE, our running time will be full exponential. There is some algorithm from Kirshner-Fook, which attacks the binary secret LWE problem in mildly sub-exponential time. So it requires the secret is binary because this type of algorithm, essentially the underlying idea is to do the collision on the AI on this number of samples, and the equivalent impact of this is to cancel some of the secrets. If there is a collision on the AI, it essentially means some of the positions in the secret can be treated as 0, and that's why it requires a binary secret. And in the standard LWE, where the secret becomes small, remember small means standard, the running time is already fixed exponential. Okay. And we can also combine this with meeting the middle type algorithm that which is useful for sparse atom E, and we will mention some of this later. Okay. And so we introduced the first two types of algorithms, and the algebraic type of algorithm is good for small e, where the combinatoric type of algorithm is for small secret. Well, the geometric algorithm, for example, the lattice algorithm, from an asymptotic point of view, is not good at all. The reason is, have a quick summarize of the asymptotic running time when Q is polynomial in N. So as long as the Q is the modulus Q is sort of standard, it's a polynomial in terms of the input N. No matter which variance we are considering, the running time is always fully exponential. But the situation is changed when Q is more than polynomial. So if Q is more than polynomial, if Q is sub-exponential, for example, well, I still keep my secret and error to be small, which means standard, the running time could be sub-exponential depending on how large Q is. So that's why that's a different regime for setting the Q. So for now, I'm just considering the polynomial Q, and with that fixed, no matter what the secret error is, the asymptotic running time of the lattice algorithm is always bad. It's full exponential. We never have the case of sub-exponential. Okay? But there are some good features of this because the number of LW samples required in this lattice attack are usually very small. And recall that many of the attacks mentioned before requires, for example, a sub-exponential number of samples, where here I only require it to be, for example, a constant times N. And that's why these algorithms are very relevant in terms of the concrete security level for NIST candidates. Okay. So before I start with the lattice of LWE, I just want to sort out, are there any questions or remarks before I move on? Okay, so keep moving. So a lattice is just really an integral linear span of n independent vectors. So here I choose Bi, each of the basis vector in Zn to be integral as well. But we can also make them to be in Qn, or the general definition also holds for larger space. But from a computational point of view, it makes sense we just consider them in Zn for the moment. And the lattice is the integral linear span of them. And I will collect all the basis vectors B1 to Bn and denote it as a matrix B. And another way to write the lattice is use the matrix multiplication. Certainly, I use the column form here. Okay? So B times X, where X is arbitrary integral. Okay. so the volume of the lattice is the determinant of this. I assume the square. So that's the determinant of this B, which is independent of the choice of basis. So we can have a unimodular transformation of the basis, but we still have the same determinant. Okay. So the focus of this lattice attack will look at invariant, which is called the lattice minimum. As soon as we are given this lambda, this lattice minimum will be fixed. So in this picture, I draw a two-dimensional lattice, which is generated by these two blue guys over here, and the minimum is given by this point, or is symmetric one over here. So it's the minimum non-zero vector, of course, because zero vector is always in the lattice. So which I will exclude. So given this lattice minimum, the computational problem for lattices that we will focus on, which is actually a variant of this that we will see later, but we will start with so-called shortest vector problem, SVP. So the input is a basis, and the output is the shortest non-zero vector in the lattice generated by this basis. And again, like the decoding problem, where you start with some good basis, and then you do some permutation of this basis, you want to get a bad basis. That's the same philosophy here. The difficulty of this problem does not really depend only on the lattice, because my underlying lattice is always fixed, but it actually depends on the shape of the input basis B. So in cryptography, we want a bad basis B. And here illustrate an example. Again, this green dot points correspond to a two-dimensional lattice generated by the blue and the red or green, depending on whether you are colorblind or not. And then we're looking at, so in this picture, we can already visually identify the blue is the shortest vector, right? But in crypto, we're not going to give this B like the blue and the red one. Instead, we're going to give these two. So this very long red and blue, which are skewed. And I claim that this generate the same lattice. If we look at the parallel in between the red and blue, probably the volume is the same as before, because here you have very small margin in between them. And in crypto, we are really given this kind of very, very skewed and very long lattices. And the task of lattice reduction that we're going to discuss later is to recover the previous basis from this one. So we're given this one through some algorithm aspects. We want to recover this one. Therefore, we also find the short vector over here. So so previously I mentioned the problem as SVP problem, where I want to find the very shortest vector S. But here, crypto will need to use a relaxed version, which I call SVP gamma. So instead of finding the shortest vector, it is sufficient to find the short vector, which is up to gamma times the length of the shortest vector. So the gamma is some relaxed factor, where gamma is normally a function of n. Okay. For example, if my gamma is exponential in terms of n, which means, okay, I can allow my relaxed factor to be exponentially large, then the triple L algorithm already solved this problem in polynomial time. However, in crypto, my gamma is normally polynomial or very slight substantial in terms of n. And in this regime, the running time of the best algorithm, which is so-called the BKZ, runs in fully exponential time or very mildly sub-exponential time. So that's the regime that we're going to consider in crypto, and we're going to relax gamma. And if my gamma is exponential, that's a bad choice for crypto, because we already have a polynomial time of algorithm. So the difficulty of this SVP gamma depends on the gamma as a function of n. Okay. In order to solve this SVP gamma, it turns out we're going to use SVP1 algorithm. So the algorithm for them are actually this reciprocal, because the SVP1 algorithm will turn out to use SVP gamma for some preprocessing. But for the moment, it's sufficient to consider that in order to solve SVP gamma, which is our crypto-related problem, we can solve SVP1 in a smaller dimension than the given n. So here is the context. So the best algorithm for solving SVP gamma, which is crypto-related here, is the so-called BKZ with parameter beta. And this beta denotes the smaller dimension where we're going to solve the SVP1. Okay, so the complexity of this BKZ beta is dominated by the running time of SVP1 in smaller dimension beta. So in other words, if I want to solve a SVP gamma problem in dimension n, it is sufficient to solve a SVP1 problem in dimension beta, where beta is generally strictly smaller than n for crypto parameters. So this is the problem. SVP1 in some smaller dimension beta is what we're going to focus. So therefore, we want to understand what is the best algorithm for solving SVP1 at dimension beta. So there are two types of algorithms, and they are different by their memory usage as well as their asymptotic time. So the first type of algorithm is called enumeration. It solves the SVP1 at dimension beta in time super exponential, 2 to the beta log beta. So this is the KFP enumeration algorithm and its follow-up work. There's a second type of algorithm which is called Lattice Cv, which is asymptotically better. It runs in 2 to the order beta. However, the memory requirement for the Cv is the same asymptotically, where the memory requirement for the enumeration is polynomial in terms of beta. So these two algorithms come in slightly different flavor in terms of memory requirement. Okay. So in the end, we're trying to link 1 and 2. So for example, if we are given a SVP gamma problem in dimension n, and this n and gamma can be decided directly from the LW problem. We will see an example later. Okay, so we want to determine the required beta in the BKZ beta algorithm for solving the SVP1 over here. So how do we determine the required beta given the gamma and the n? So the relation it has to satisfy is the following. We need the beta to satisfy this relation. So where we can think of this gamma and the n are driven from the crypto schemes, they are fixed. So we need to choose the smallest such beta, which satisfies this equation over here. So this beta is so the right hand side is dominated by beta of 1/2 beta, which is a decreasing function. So for large enough beta, this should be satisfied. So we're going to find the smallest such beta satisfy this equation. Okay. So therefore, we can decide beta from the crypto schemes, which give us gamma and n. And once we got beta, for example, beta is 400, and we can plus beta into this asymptotic notation over here. And clearly, we want some more precise estimate for this in addition to the asymptotic one, and we're going to consider that. Okay. There is a related problem, and there's a caveat, because the problem we are trying to solve from LW is so-called the unique SVP problem. And the problem gives actually the lattice problem converted from the LW is a special kind of SVP problem. We know that the second shorted vector of the lattice divides the first, the very shorted vector has a gap. It's larger than gamma. And the goal is to recover the shorted vector from this special lattice. So this B is special in some sense because it has a gap, where the SVP problem that we mentioned earlier works for any lattice, where this problem has to define on a special lattice where it has a gap. but it's okay to consider because there's a reduction to uSVP gamma to SVP gamma. So if we can solve SVP gamma, we can solve this. So therefore, it is sufficient to just consider this model and treat uSVP gamma to be either the SVP gamma. Okay. So we're going to think about how to convert LWE into a lattices. And it's very close because the LWE and the Cis problem, they are given a matrix form. So it's column space and it's kernel space. It's almost like a lattice. So and concretely, we will need the two following lattices, where A on the left-hand side corresponds to the tall matrix in the LWE, which is the generator matrix of a code in the transposed form. And this B is the matrix for the Cis problem, where I'm going to consider a slightly different lattice. Okay, so the very first lattice that we're going to consider generated by A is really just the column space of A together with the Q. So Y is the set of all the Y, that Y equals to AX, where I'm considering all X. So it's a set of all the Y such that Y equals to AX over all the integral coefficients X. And this Y is over the full space Z, because as long as Y equals to some AX mod Q, then that's okay. So Y is not restricted to be Q. Okay. So this is the first lattice, where the lattice corresponds to the set of all the points Y over here. And in the second lattice is we call it the kernel lattice. It's the set of all the points E such that B times E equals to 0 modulo Q. It's the set of all the E which makes B equals to 0. Clearly, we also have to include the information of the Q into the basis of this lattice. And there are explicit ways for constructing the basis for A, lambda A, and the lambda orthogonal B here. And there are some relation of these two lattices. They are almost due to each other up to a constant. Okay, so we will refer them to be either the column or image lattice or the kernel lattice on the right hand side. And in the follow-up attacks, we're going to use some of the alternative. Okay, so the very first lattice attack for LWE is presented as a decoding attack. So in the coding language, this is more like we are trying to recover the code word, given the transmitted code word, which is biased. So that's really where the language comes from. Okay. So the main idea is the error is short. It's still much longer than the coding sense because you cannot decode correctly or easily, but it's short enough that you can still have a unique solution. So the image lattice that we defined before is the set of all the Y such that A times the integral coefficient X. So the idea is that this Y is some of the Y is almost close to the given target point B because they are B equals to A S plus E, where S is a particular X over here. So therefore, this Y, some of the Y is differed by this B up to a distance of E. So therefore, the idea is to solve some closest vector problem or some bounded distance decoding problem. So the lattice generated by this column of A has rank M because if I look at this Y, it has length M, and it's known that it has volume Qm minus N, where M is the number of rows in A and it's the number of columns in A. So we can convert that problem through some embedding method that I will mention later. But so far, the concrete security actually depends on the number of samples M given. So in terms of the best asymptotics, we need to set M in some optimal way, such that m is about n log q divides log of alpha inverse. Remember, this alpha is the noise rate. Alpha q equals to square root of n, for example. So this alpha is smaller than 1. That's why we have the minus over here. So if I plug in this optimal m, we can get the asymptotic running time given this. Okay. So which is expressed as the parameter of LWE is n log q log squared alpha to the same thing, to the n log q over log squared alpha. That's why the binary secret LWE does not change the asymptotic that we mentioned earlier, because we can plug in the binary error LWE where the alpha can be considered as the, for example, as a constant divides the q, and the q is a polynomial n, and if we plug in this thing over here, we can see that's still full exponential time. Of course, this asymptotic running time is not really too interesting from a practical point of view, and we're going to have a practical method for estimating this in the next page. So I will just briefly go over this condensing embedding. So the idea is we express B equals to AS plus E plus CQ, where B is close to the so-called QRA lattice generated by AS plus CQ up to a point E, where E is the small shift. It's like the error in the coding. Okay. I will take a lattice L as the basis of this AS plus CQ as a lattice. So I will generate a slightly larger lattice, which is just larger by extra dimension over here, which is LB01, and we can see that L prime times some this star one, where this star is the solution for getting the AS plus CQ, which is closest to B. So this star is really just hidden over there. If I use L prime times that, it recovers E1, and therefore E1 is the shortest vector in this L prime. That's how we turn the BDD problem in a uSVP, SVP problem. But this does not really change the estimate too much, because it only increases the dimension by 1, and it does not increase the volume. Okay. And here is a practical method for estimating the LWE with respect to this decoding kind of attack. So the idea is, given the parameters NQ alpha in LWE, we just try, in order to find the optimal M, previously there's the asymptotic value, but now we just try all the M up to some bound. This can be just a small constant of times N, so that should be practical in practice. Okay, so first of all, given the LWE problem B equals to AS plus E, I know the shift is the error E. So is L2 norm E, I know it from either the description of the algorithm or the description of the scheme. So I can have a fairly good estimate of the L2 norm of it. Okay. And then the uSVP problem that we mentioned earlier will have the following gap, where the E is believed to be the shortest vector in this lattice, where the second shortest vector in the lattice is normally estimated from this Gaussian heuristic, which is given by this guy. So you can see that this M, N, Q are all fixed given the LWE problem for fixed M in this loop. Okay? And once we derive this gamma, which is just a real number now, I can take my gamma to the 1 over m's power and find the smallest beta according to the previous method. And now beta is some number. So for example, 500 or 400. And then based on that, I can plug that into the running time. Remember, there are two algorithms. The first algorithm is enumeration. The second algorithm is sieving. So here I simply plug it into the sieving because sieving has a smaller asymptotic running time, and it's 2 to the big O beta. But here I plug in to the concrete complexity that we will also discuss later, which has the small constant 0.265. This is not precise because we will see later There are some more precise estimate on this. Okay, we just choose the smallest beta over all such m. Okay. And this method is almost close to the method in the lattice estimator that you can find online. Not exactly the same because there are some tweaks on this, but they are almost similar. Okay. There is a second method for solving this LWE problem, which we are converting to a lattice. The method is really this that we mentioned earlier. We look at the equivalence of LWE versus the cis problem, where I times the B by the left kernel of A. So this AS cancels out. The only information left out is this E. So I have A times E equals to some T. So I denote this A kernel to be B. So I have B times E equals to T, where T is A kernel B modulo Q. So again, this is a cis problem where I'm trying to find that we only have to look at the set of all the E, which is the second lattice, which is the kernel lattice, which is the set of all the X such that B times X equals to 0 modulo Q. Okay. So the way to solve is first of all, we're going to find some arbitrary Y such that by equals to T. So we can compute this by linear algebra because Y does not have to be small. So this is different to the cis problem, BE equals to T, because I need E to be small. So here I just find some arbitrary Y. Okay, so Y can be very large. This can be done by linear algebra. And once I did that, I will find some V, where V is some lattice point in the kernel lattice, which is closest to this Y. Okay, so V minus Y is short. And given that, I also know that BV is equals to 0 because V is a lattice point over here. Therefore, I have two relations, BY equals to T and BV equals to 0. So I subtract these two equations. I have BV minus BY, where V minus Y is short. So I have BE equals to T. So I find a short solution on this. So I simply find the solution within the kernel lattice. And this lattice, kernel lattice, also has some no volume and rank. And the behavior of this attack is only the information on E is used over here. Okay, so this is sort of similar to the previous attack in the sense that also only the information of E is used. Okay, and in both of these two attacks, we can see since the information on E is already used and information on S is dropped. So somehow this may be good or maybe bad, depending on the size of S. So there is yet another attack, which is similar to the kind of systematic form of some larger A. So I simply combine A and the identity matrix and combine S and E. So I have A and M times SE concatenated equals to B. Again, this gives me a new kind of a cis-like matrix A. So A prime times S prime equals to B. So the task is to find SE in the kernel lattice formed by A prime. So that's exactly the same as before, except I use a wider matrix A prime. Okay. It looks like that this method, if SE is short, it looks like this method is equivalent as before, but it's actually slightly different if the number of samples given is restricted. So if I'm giving a fixed number of A, the underlying impacts of this method is that it looks like it grows the number of samples in some sense because the rank of this lattice is increased to M plus N. And remember, previously we mentioned that there's an optimal M. It turns out that will have an impact on the optimal dimension of the lattice. So we have some slightly more room for choosing the rank of the lattice in this case, depending on the parameter. Okay, and if S and E is not balanced, we can rebalance the lattice in some method. Okay, so As a conclusion, these methods are sometimes equivalent, but not always. That's really because of there's a, as I mentioned, there's a kind of a messy situation in setting up the parameters depending on the given samples as well. Okay. And in addition to that, there's also a kind of a hybrid strategies which combined with the lattice reduction I mentioned with some combinatoric type of algorithms. And these are really originated from some of the work on N2, where the authors combine the lattice reduction attack with combinatoric kind of meet-in-the-middle attack. And there are follow-up works on applying this to the LWE context. Okay, clearly, they sometimes give a better algorithm, which is normally the case when S and E are sparse, because that's where the combinatoric type of algorithm are mostly effective. Okay, and in the end, I would like to mention some of the concrete complexity for solving SVP1 of rank beta. So previously, we treated as an oracle just by saying there are two types of algorithm, enumeration and sieving, whose running time is 2 to the OB and 2 to the order B log B, beta log beta. But now we want to look at their concrete security. So, in terms of the sieving, there are two words. In the classical world, is this guy plus some small order term. And in the quantum world, it's 2 to the 0.265 beta plus small log beta. Okay, and this is a slightly more precise estimate than the 2 to the big OB notation. And the simulated complexity for the classical one is given. So I can only find this in this paper, and I think there are this is some there are some debate on this on trying to derive the small order beta over here, and this is one of the central problem for the concrete parameter for the NIST proposal. And for the enumeration, similarly, we have the super kind of exponential expression on the running time, which is 2 to the this concrete number plus some little O1, and for this one as well. And these numbers are really just from some heuristic estimate, and we can actually improve the algorithm from the 0.187 to 0.125 plus still some little O1 term. So far we are not considering the simulated result at all. It's just some theoretical estimates based on some heuristics, for example, the Gaussian heuristic. But this faster enumeration will be based on the case where the n should be not too small compared to the beta, where the original enumeration, the KFP enumeration, works for any beta, regardless of its relation as n. For example, beta could be the same as n, where in this variant algorithm, we need there some slight room for pre-precise the SVP beyond the beta side window. That's why we need n to be larger than asymptotic larger than this beta. Okay, so the idea is to precise in some larger region. That's why we need this n to be slightly larger than beta. Of course, in the asymptotic sense, these algorithms are not really used for the NIST parameters, but in the practical sense, we can also simulate the running time of this algorithm, and that seems to give this simulated complexity where n is a constant times beta. Okay, so really that's because this log beta is also very small in practice. Okay, and this 0.547 beta plus 10.4 is some simulated result for this little O1 terms over here, times beta log beta, of course. There's also another improvement which is practical in the sense because it does not improve the asymptotic estimate, which is this 0.128, but it improves slightly this little O1 term, which decreases from 547 to 654. Okay? So the idea is to use some approximated SVP solver inside this SVP1. Okay, and in the end, I'm going to discuss some questions. So first of all, it seems to me that there are lots of discussion on hybrid attacks applied for untrue, but there are fewer kind of work on hybrid attack to LWE. In recent years, I saw there are some good work on this, but still, I think there should be a more comprehensive study of this hybrid attacks to LWE. Also, I mentioned there is a gap between the best reduction and the best attacks invariance of LWE. In particular, there are some regimes of parameter where there's no reduction, and still the best attacks are exponential. So in this regime, it may be interesting to look at their relation, whether there's a better attack or whether we can actually reduce them in the theoretical sense. Also, the running time of BKZ beta, for the moment, it's estimated using the so-called SVP core model, which is the one that I mentioned earlier. In order to solve SVP beta, we just think about its running time the same as solving SVP1 at the lattice beta, but that's just a very kind of crude or coarse lower bound estimate. So we want to estimate this time more precisely. Okay. There's also a kind of interesting research on the relation between sieving and enumeration, because the sieving is better than enumeration in terms of the speed, both in theory and practice. But there is some speculations on whether the memory can be still feasible for larger size, because the memory of this sieving is exponential. So that's really well, the enumeration only requires a polynomial memory. So that's some hot topic. And whether we can find some algorithm in between which does a trade-off between sieving and enumeration, that could be interesting. And whether we can devise some algorithm which is better which is BKZ-like but better. This is also related to the question of how to estimate the running time of BKZ beta better. Okay. Again, in this talk, we never think about the algebraic structures at all, where most of the NIST proposals use algebraic structure. So whether we can better take the algebraic structure into consideration in lattice reduction, that's a very interesting question. Okay, that's the end of my talk. So thanks very much.
Thank you, Shi.
Thank you.
It was a very nice talk.